last time we were dealing with the idea that we had neutral acids that had negatively charged conjugate bases versus positively charged acids that have neutral conjugate bases. We had previously noted that hydronium and protonated alcohols or oxonium ions have a pKa of -2, but then there's another acid-base equilibrium after that, and that's for their conjugate bases respectively, the water and the alcohol, to themselves lose a proton to become hydroxide and alkoxide. And we had noted a pattern where, as with all polyprotic acids, the first proton you lose is the easiest, and then the next one after that is more difficult. And again, it's about 10 to the 18 times more difficult to remove a proton from water than it is to remove a proton from hydronium. Similarly, we'll see that the next door neighbor of water and hydronium are these ammonium ions. So the ammonium ions are the nitrogen analogs of hydronium, and they are positively charged acids that have neutral conjugate bases. The ammonium, there are ammoniums with 3 protons, 2 protons, and 1 proton. They're all positively charged. They can each lose a proton to become various kinds of amines with 1, 2, and 3 R groups respectively. And the pKa's there are about 11. I didn't put on this list, because it happens to have a slightly different pKa, just NH4+, which has the conjugate base ammonia. This is also an ammonium ion, but its pKa is a little bit lower, around 9. And I won't worry about the explanation for why that is, but that's why it's not necessarily on the list. Okay, so pKa of 11 to go from positively charged ammonium to neutral amine. I'm making a big deal out of this because this is something that people will get wrong on the exam. Yes?
So just to make sure I got this straight, so the lower you go in the pKa, the stronger it holds on to its electrons, but the easier it is for it to donate photons?
A lower pKa means the conjugate base is more stable. Electrons on the conjugate base are lower in energy, but it also means that the acid is stronger and more readily loses a proton. Yep, good. So just as the neutral conjugate bases of the ammonium ions themselves can lose a proton. 2 of the 3. This one actually doesn't have a proton on nitrogen to lose. I'm making a big deal out of this because people will use the wrong pKa for these neutral conjugate bases losing their additional proton, and it makes quite a big difference. So you want to sort of pay attention to this so you don't make the same mistake. I'll write it here. We may need to move these items down the list in a little bit, but the neutral amine RNH2, or its cousin or sibling, whatever, where you have 2 R groups and only 1 proton, that pKa is 38. All right? So that's a huge difference, a factor of 10 to the 27 or something like that. You can see how if you got that number wrong, you'd make some vastly different predictions. The neutral amines have negatively charged conjugate bases where the nitrogen has a negative charge on it. And these negatively charged conjugate bases kind of are called amides, kind of like you got hydroxide for water. Okay, so losing from the neutral amine to the negatively charged amide is a pKa of 38. And that makes a big difference. So let me illustrate that with an example. So we're going to use, and this will be an example of how to use how to use pKa information to predict acid-base equilibria. Sure. So in an acid-base equilibrium, and I'll show you actually a mechanism for this. It's really kind of easy. You can identify, you want to identify the acid and the base on one side of the equation. So here it's pretty clear the positively charged thing with protons on it should probably be the acid. And the negatively charged thing should probably be the base. I'll point out just at this stage that a Bronsted base, which is you've learned as a proton acceptor or a proton stealer, is also a nucleophile, is also a Lewis base. In fact, you're going to see that Bronsted bases are just a special class of nucleophiles in general, kind of like all squares are rectangles, but not vice versa. We'll see that all Bronsted bases are nucleophiles. Okay? In the same way, this Bronsted acid that's a proton donor is a Lewis acid, and the empty orbital, it's a Lewis acid and is also an electrophile. The empty orbital that's going to accept electrons is the nitrogen-hydrogen sigma star. Now, at some point in the past, there were a few study guide examples where I gave you things like an alcohol or hydronium and was asking you to think about HOMO versus LUMO. And the answer in the study guide was in some cases that the oxygen-hydrogen sigma star would be the LUMO. You didn't know how to predict that was the case. We're now sort of learning how. The pKa information is going to tell us when we have low energy nitrogen hydrogen sigma stars or oxygen hydrogen sigma stars, because what happens in a typical acid-base reaction between a Bronsted base and a Bronsted acid, or between a nucleophile and an electrophile, is simply that electrons from the negatively charged atom on the Bronsted base attack the nitrogen-hydrogen sigma star, break the nitrogen-hydrogen bond, but make a new bond between oxygen and hydrogen, okay? So that's how the reaction happens. The products here are the amine conjugate base of our ammonium acid and then the alcohol conjugate acid of our alkoxide base. All right? Presumably, you had some experience identifying conjugate acids of various bases and conjugate bases of various acids. Sort of, maybe? No, totally new. Yeah, go ahead.
So those are both Lewis acids on the left?
No, I meant Lewis base, thank you. How long were you guys going to let me do that? Snickering to yourselves, look at what he did. Yeah.
So after the oxygen breaks that bond between nitrogen and hydrogen, where does the hydrogen go?
Yeah, the hydrogen goes after the oxygen breaks the bond between nitrogen and, hydrogen. That the new bond is here. This is the proton that got stolen. Okay? We call this an acid-base equilibrium, but we also call it deprotonation. Okay?
Electrons that were donated by the base are left on the nitrogen as a lone pair.
The electrons from the base are now in this bond between oxygen and hydrogen. The new lone pair, let's say you need a different color, don't I? The lone pair on the nitrogen used to be in the nitrogen-hydrogen bond. Yep. So, yeah, okay. So now, if I were to ask you which side is favored at equilibrium, that would be the same question as asking you which acid is stronger, the acid on the left or the conjugate acid on the right. And that is actually also the same question as, is this base a strong enough base to remove the proton from this acid or to deprotonate the acid. Okay? I will just point out briefly that when you learned about acid-base equilibria in general chemistry, you sometimes talked about acid dissociation, which was actually shorthand for something that's going on in aqueous solution. Protons don't just fly off into a vacuum. For our purposes, there's always going to be a base that removes the proton. And I will show you a little bit later today, hopefully, how that was actually happening all along when you talked about dissociation of strong acids in water. But in any case, the question as to which side is preferred at equilibrium is the same question as asking, is this base strong enough to deprotonate this acid? And that's exactly the same question as asking which acid is stronger. Okay? So to make that determination, we simply look up the pKa's in our pKa table. I happen to have memorized that the pKa for the alcohol of our conjugate acid, that pKa is 16. Now, here's where you can make the mistake. I look at the ammonium ion. If I go here and I say, oh, my conjugate base is an amine, and I find the neutral amine, and I go ahead without thinking and write down that number, I'm going to get the question wrong. Okay? So this is not the right number. I will show you in a moment. I'm not going to bother doing the problem with the wrong number because I don't want to deceive anybody, but we're going to find out how to look up the right number, get the question right, and then we'll see how using the wrong number would have gotten the question wrong. Right, so too many wrongs and rights. Here is the positively charged ammonium ion. Again, I'm sorry I'm beating this into the ground here, but some of you are still going to make that mistake on the exam, and I am trying to shake my clothing in front of you so that I can be free from your blood when you go to take the exam. Thank you, Jacob in the Book of Mormon. All right. Spiritually inspiring insofar as the subject matter permits, right? You can put that next to your evaluation all the times I tried to do that and failed. But Star Wars references, right? Okay, sorry. Anyway, positively charged ammonium ion, pKa 11, going to neutral amine. That's what's going on in this reaction, so that's the pKa that I want, is 11. All right. Now I simply compare the acids, and the strongest acid loses its proton. Sure. Go ahead.
So you got the 11 based off of the positive charge, right?
Yes. Got the 11 because I'm looking at this acting as an acid, losing a proton from the positively charged to become neutral, and that's not what's going on here, but it is what's going on there. All right, so strongest acid wins by losing its proton. That means which side? Who's the stronger acid? Water or the alcohol or the ammonium? The ammonium's the stronger acid, so equilibrium favors the right-hand side. Okay? Do you see how you would have got that wrong if you had used 38? If you use 38, you pick the wrong side as being the weaker acid. Yeah?
Do we need to memorize all the pKa's for all the...
Do you need to memorize all these pKa's? No. If you teach the class for 10 plus years, you would get that in your brain, but all you need is the -2 and the 16 and know what those mean. The rest will be in a table that will be on your exam. Yeah. Yeah. Is it the same table that's on the study guide? Should be close. I can look at it. And if it isn't, I'll post. Everyone always wants to see the exact copy of the pKa table that will be on the exam to avoid anxiety, and I'll make that happen. Yeah. Okay. Good. So, right, you've got to make sure you get that comparison correct. And understand that this question, as we've gone through it slowly, I've formatted it in just one way, which side is favored at equilibrium, but you can do this in multiple different ways, and it's all asking the same question. So Let's see, one option that's always fun that people hate is if I draw a large and scary molecule. Okay, and then I have lots of different things on the molecule. I really delight in these kinds of questions, actually. They're very fun. And then I ask the question, I have a list of bases, and I'll even make this in pseudo multiple choice format for you. Circle the options so you know, okay. And then I'll put various bases and I'll ask the question, which base, I'll ask, for this particular base that I've drawn, is it strong enough to, which of these protons can this base remove? What are you talking about, all right? Do you remember how I told you before that asking which side is favored at equilibrium is the same thing as asking, is this base strong enough to remove this proton? Is the same thing as asking which acid is stronger, okay? Note that the alkoxide base was indeed strong enough to remove the proton from the ammonium because, you can tell that because the conjugate acid of the alkoxide base had a pKa greater than that of the ammonium ion. Some of you are going to want that in words and try to memorize a sentence, and I can say it for you again. But in general, a base can remove a proton whose conjugate acid, see, this is why I don't like to put it in words, I just like to draw it. A base can remove a proton whose pKa is less than that of the conjugate acid of your base. Let me say that again a couple of times because that's going to be difficult. Well, all I'm doing is really summarizing this example that we've gone through. But a base can remove a proton whose pKa is less than the pKa of the conjugate acid of your base. Okay? That's just another way of writing out this equilibrium and deciding who wins. Go ahead.
And so it doesn't matter how strong the base is, like all these different equal.
Does it matter how strong the base is? Yes, the thing that matters is the pKa of that base's conjugate acid. That number tells you how strong the base is. Yeah. The pKa of the conjugate acid tells you how strong the base is. That's another way of saying this. Okay, so let's start with, I've written down a couple of bases that may seem a little bit unfamiliar. Let's start with this alkoxide base. We're going to first draw its conjugate acid and write down the pKa of the conjugate acid, which is what? 16. That's in your brain. If it's not, you should memorize it before the exam. Now, I'm going to go through and look at each of these acid groups and see from my pKa table what the pKa's are. Right? So, let's see. This A group is a sulfur-containing molecule. So let's scroll up and see if we have any. It's got a proton on the sulfur and it's neutral. So let's look and see if we've got anything. All right. There we go. pKa of 8. So on my drawing, I'm going to write down pKa equals 8. Going here, this looks like I need to develop some skills here. I'm not going to look at that and think, oh, that's 16, that's an alcohol, because I have something on the pKa table that resembles it more closely. This is a carboxylic acid, where adjacent to the OH group, you've got a doubly bonded oxygen. And in the conjugate base, there's a chance for resonance, right? So scrolling back up to our list, I find the carboxylic acid pKa of 4. And I could do, okay, here's an alcohol, pKa of 16. Actually, yeah, that's fine. positively charged nitrogen with a proton on it. Again, I'm gonna not use 38 because that's for a neutral nitrogen going to a negatively charged nitrogen. I'm gonna use 11 for a positively charged nitrogen going to a neutral nitrogen. So that's pKa of 11. Whoa, what about this guy? This guy's not actually on our list yet. This is an alkyne. And it turns out we can add it to the list. It goes somewhere between the alkoxide, the alcohol and the amine. It turns out that an sp hybridized carbon-hydrogen bond is more acidic than most other kinds of carbon-hydrogen bonds. The pKa is really high, but it's not as high as for some other alkanes, other carbon-containing compounds that maybe I'll show you in a little bit. So that pKa, you could look it up. This is going from an alkyne that's called an acetylene to its conjugate base that's called an acetylide, pKa of 25. All right. Okay, so I would need to recognize that group and write down pKa of 25. So now I'm just going to go through and see, okay, a base can remove a proton when the conjugate acid of the base has a pKa greater than that of the acid in question. So now it becomes greater than less than question, which you can do, right? Now we're back to, when was that, second grade, third grade maybe? All right, so let's just check off the ones whose pKa's are lower than 16. So yes, it's reasonable to remove a proton whose pKa is 8. Totally reasonable to remove a proton whose pKa is 4. 16 versus 16, that would mean the equilibrium constant was about 1 for this reaction. People always worry about getting in this situation and getting in my head and asking, what am I thinking? Is partially removing the proton enough? That is why when I write these questions, I ask which base can mostly deprotonate, where that means that, greater than 50%. So I would, and frankly, I'm going to be on your side a little bit. I would give you a base that's got a pK that's a little bit higher than that, so it's just not a problem, right? So I would say if the question said mostly deprotonate, where mostly deprotonate means greater than 50%, I'd put no on that list, okay? 11 versus 16, sure. 25 versus 16, no. To get it? Okay, good. Practice that. We don't have a lot of time to go through examples. You're going to need to do that on your own with examples from the study guide and from the practice exam until you can do it every time without trouble. Don't trust yourself. I mean, we've kind of brought it down to the level of greater than, less than, which seems easy. Don't trust yourself until you've actually put it into practice. You need to be the one looking stuff up in the pKa table, making sure you get it right. Yeah?
So would B be the one that mostly deprotonate since it has the lowest pKa?
No, for this question, yeah, would B be the answer? No, I suppose if you asked which of these protons is more acidic, B would be the correct answer. This is a multiple response question. I say which of these protons can be removed by the base. To get this right, you need to select A, B, and D, but not C and E. Yep. Yes?
What's the context of the other bases that you, or the other molecules you put next to the base?
Oh, sure. So what would this be if we tried, I'm going to erase our orange check marks so that we can do this question again. Yeah, I intended to do that. What about those other bases? It turns out, and this would be in your table, I haven't listed it above, H minus is called hydride, and its conjugate acid is hydrogen gas, which has a pKa of around, I'm writing pKa's in blue, forgot, which has a pKa of 35. You can actually buy, you can't buy H minus, you can't buy anything that's just totally negatively charged on its own. You need a counter ion, but I haven't written that because we're sort of ignoring it. You can buy sodium hydride. It is a salt, it is solid, and you can use it as a base in organic reactions. But with this number 35 present, how does that change the answer to our question? Could it deprotonate A? Sure. B? Yep. C? No problem. D? Yes. And E? Yes. Okay. And then similarly, we won't go through it as slowly as that for the NH2 minus base, but if you go back up to the pKa table and find the NH2, I guess I should have included NH3 going to NH2 minus here. That pKa should be 38. And again, you know, you got the same sort of issues. 38 is greater than any of those numbers. And so yes, you would say this base is strong enough to remove all those protons. This has some synthetic chemistry implications when you're in the lab and you need to remove a proton to do something. You want to use the appropriate base. You also would want to be aware of potential undesired side reactions. So supposing I wanted to just remove this proton and none of the others, that's going to be pretty hard to do with just straightforward acid-base chemistry. And we'll see, you'll see later on in 352 that we have a strategy in OChem called protecting group strategies, where we install other pieces of molecules on any of the groups that we don't want their protons to be removed, sort of shielding those groups. Then the only acidic proton in the molecule is the one we want to deal with. That's just a preview, but being aware of these issues is really important for an organic chemist. Okay, good. So you got to practice that, because we can do it in class, and I know it makes total sense now, but when you're alone in the testing center and the person next to you is crinkling some wrapper or sniffling, and you've got your molecule set all over the desk and spilling, and it's 5:30 in the evening and you haven't really eaten since breakfast and you're really stressed out, all of a sudden what made sense right now while you're sitting here is no longer going to make sense. So give yourself some practice, build in some muscle memory, make sure you can do this. I guarantee you there will be a molecule on your exam that you will think it looks like this. There's going to be actual bonds here in place of the angry face, but it will look something pretty similar to that. Okay, so I want to take just a minute. We've talked all along about the whys behind the pKa trends. You need to be aware of those. Remember electronegativity, size, resonance. I mentioned something about the alkyne that I just want to illustrate briefly. The pKa of the alkyne, as I said, going to the acetylide is 25. If you go to not the alkyne, but the alkene, that pKa is around 40. So just changing the hybridization from sp of the atom that's going to bear the negative charge in the conjugate base, just changing that hybridization from sp to sp2 dramatically changes the pKa. And if we go to the corresponding alkane, I'm just going to use R groups willy-nilly here so we can focus on one proton. That pKa of the proton is around 50. Okay? So that's what changes when you have a carbon in the conjugate base that goes from sp to sp2 to sp3. All right? Why do you think that makes such a big difference? Go ahead.
Because pi bonds are less stable than sigma bonds.
Is it related to pi bonds being less stable than sigma bonds? I mean, I'd say probably not directly, though you're on the right track. Why is a sigma bond more stable than a pi bond? Okay, energy difference, good. And sigma bonds hold electrons closer to the nucleus, right? What do you know about s versus p orbitals? S orbitals closer or farther from the nucleus? Closer, right? The s orbital actually has, the wave function has finite value at the nucleus, whereas for the p orbital, there's a node at the nucleus, right? So orbitals that have more s character, orbitals with more s character are lower in energy. You can almost think, which means that a negative charge on an sp hybridized carbon is more stable than a negative charge on an sp2 hybridized carbon, and so on. You can think of sp hybridized carbons as actually being more electronegative than sp2, and sp2 as being more electronegative than sp3. Because really electronegativity is all about how low in energy is a pair of electrons on an atom, okay? So these are some numbers that we will see. Again, they would be on your pKa table. But that's an illustration, again, of the electronegativity principle of how increased electronegativity of an sp hybridized carbon makes the corresponding conjugate acid more acidic. One more trend we need to, go ahead. That's right, because in the conjugate base, the electrons are closer to the nucleus for the alkyne than the alkene or the alkane, that the conjugate base is more stable and the acid is correspondingly more acidic. Right, for I minus, wouldn't the electrons be further from the nucleus? Yes, though it's kind of a potential energy versus kinetic energy argument. Closer to the nucleus is lower in potential energy, more spread out is lower in kinetic energy, and so there's a trade-off. And in terms of how you navigate that, we say within a row of the periodic table or on the same atom, the electronegativity issue is biggest. Down a column, the size and kinetic energy issue is the biggest one. Column versus row, yeah, that's the best way to deal with it. Good. All right, one more thing to just, and let's see, do I have actual numbers? Yes, good. One more principle for, and it's related to electronegativity, but it's a little more complicated than that. One more reason why some groups can be more acidic than others, and one more why behind a trend in pKa's we'll illustrate here. The pKa of acetic acid on the left, or vinegar, is 4. The pKa of trifluoroacetic acid on the right, we have this molecule in my lab, and we use it all the time. It's quite a bit more reactive than vinegar, and it's reactive enough that you would not indeed want to put it on a salad or a sandwich, is more acidic. Now, if we look at the conjugate base, the negative charge in each conjugate base is held on the same kind of atom. And though I'm not going to draw the resonance structure, I'll use pink highlighting to indicate that both are resonance stabilized. The negative charge on both oxygens can be delocalized, on both conjugate bases can be delocalized onto the other oxygen. So what's the difference here? And it's the presence of these fluoro groups adjacent to the carbonyl, or the carbon that's involved in the double bond to oxygen. We'll call this carbon that's adjacent to the doubly bonded, the carbon that's doubly bonded to oxygen, we'll call this the alpha carbon. Organic chemists tend to assign Greek letters to atoms to identify how far away we are from some reference point. So if this carbon is our reference point, this is the alpha position. If we went one more out, that would be the beta position, and so on. So for the trifluoroacetic acid, the alpha carbon has fluorines on it. For just regular acetic acid, the alpha carbon just has protons on it. Now, you know fluorine is more electronegative than carbon, so it would be straightforward to predict that there should be dipoles, bond dipoles, pulling electron density away from the alpha carbon and toward the fluorines. You ever seen that symbol before in general chemistry? That's a vector symbol for a dipole. The little cross at the end indicates the positive end of the dipole. It's the same thing as drawing a delta minus here and a delta plus on the alpha carbon. You got 3 of these. Each of the fluorines is pulling electron density away from the alpha carbon. That makes the alpha carbon itself electron poor, and for all intents and purposes more electronegative than our reference carbon. So now the alpha carbon in turn is going to pull electron density away from that reference carbon, which in turn is going to try to pull electron density away from the negatively charged oxygen. This kind of thing where we're pulling electron density away through the sigma bonds between atoms, this is called an inductive effect. Or your text may call this inductive withdrawal of electron density due to nearby electronegative groups. And this is why am I writing it out like this? I don't know. The issue is that some people will look at this and say, why is the trifluoroacetic acid more acidic than regular acetic acid? And they'll say, oh, it's electronegativity. Well, not quite, because the electronegativity of the atom that bears the negative charge in the conjugate base is the same. What's different here is at an adjacent position, you have electronegative groups that can shift the electron density of the molecule, pulling electron density away from the place in the conjugate base where there's a lot of negative charge, okay? And so this is an example of delocalization. We're delocalizing some electron density by pulling on it with electronegative groups. This is not the same as resonance. We've had resonance delocalization. We've had delocalization because you're on a large atom. This is the third kind of way, and it involves just spreading things out because of nearby electronegative groups. Okay? Yes? What is the shape of the group with all the fluorines? It's the same as the group without the fluorines. That's a sp3 hybridized carbon tetrahedral. Is that what you're asking, or no? The dipole moments don't cancel out because you need 4 of them to cancel out. If it were tetrafluoromethane, it would be the same. Yeah. Okay. All right. Now I want to just show you something that's going to be useful when you are in biochemistry and useful if you're in biology or biochemistry lab. But to do this, we have to go back and think about what we really meant by acid dissociation in the first place. Apparently, either it's the day of Pentecost and we're hearing the sound of a rushing wind, or the air system is blowing loudly through the vents. I'm going to guess it's the latter, though. I mean, if you're feeling the Spirit, that's great, because the Spirit testifies of all truth. Okay, so you've seen this kind of thing before. You were told that pKa or Ka was your acid dissociation constant because you go from HA to H plus and A minus. I'm telling you, you were oversimplified too. What you were told was true from a certain point of view. 2 Star Wars references, 2 lectures in a row. That is great. If you don't know that that's a Star Wars reference, then you should go learn some stuff about Obi-Wan Kenobi in all of your spare time. The equilibrium constant for this reaction would be H3O plus times A minus divided by HA over the the concentration of water. Now, before you were probably, water was sort of left out of this, and but you don't have to. And by the way, when HA dissociates, the proton is not going off into the ether somewhere. It's actually being removed by the water. The water is acting as a base, and you're attacking the HA sigma star, and you're losing the proton, and then A minus leaves with its electrons. Okay? So this is what the real equilibrium constant is. Now, the concentration of water in an aqueous solution is around 55 molar, and it doesn't change a lot, even though some of the water is becoming hydronium. So we can treat that concentration as basically constant. We can move it to the other side of the equation, and then this is our acid dissociation constant, Ka. So you've seen Ka before, and maybe you put hydronium here, maybe you put H plus there, but this is what was actually going on. All right? Now hang in there, because we're going to do a logarithm, and I'm sorry. pKa is the minus log, base 10 log of Ka. So now you need to know some stuff about properties of logarithms, which we're not going to review, but everything I'm going to show you here works. Oops. With me so far? The logarithm of a product is same as the sum of the logarithms. Yes? Yeah? Sorry. So we can actually rewrite this as minus log of hydronium concentration minus log of the ratio of A minus over HA. Or, now we remember minus log of hydronium concentration is pH. I'm hearing people whisper some names that start with H. Oh, that's the Henderson-Hasselbalch relationship. Right. Derived here for your very consumption. I don't know. Ta-da. And if you want, you can reformulate this as pK equals pH plus log of HA over A minus. You can have whatever form you want. Now, you may have used that before in a different form. You may have actually moved all of this to the other side of the equation, put pH here, and then someone could ask you, you have 7 grams of monosodium phosphate and 25 grams of disodium phosphate, and you mix them together and then put them in water. What is the pH? You've seen a problem like that before? Okay. All respect and love to my colleagues who taught you general chemistry. That is boring. So boring. Actually, it's useful if you're working in a biochem lab or if you're working in my lab, you want to prepare a buffer. You know exactly what amount of acid and its conjugate base to prepare to get pretty close to the pH. That's really useful. But I'll show you an even funner, more fun, better useful form of this equation. And that is to look at, oops, didn't want that. pKa minus pH equals log of HA over A minus. Okay, why are we doing this? Behold, a large biomolecule, which is friendly instead of scary. But it has lots of functional groups on it, things that some of which you've seen before, some of which are in your pKa table. Da, da, da. And there are other groups I could put on there. I tell you pH equals 7. And then I ask you, what is the total formal charge on this molecule at a pH of 7? This equation is your key to answering that question, though it really is exactly the same as this question we dealt with a long time ago. So you would need to go through and identify pKa's of the various groups. I'll write down some that I know from the table. All of them that I know from the table. You would need to look those up, right? And that's okay, but you need to practice that. But I'm going to compare pH to pKa. What does this equation tell me? If pKa is greater than pH, which form dominates, acid or conjugate base? We'll let you noodle on that, properties of logarithms, until next time. All right, we'll see you Wednesday.